midterm covers the following sections. Chapter 9, no, that was practically, that is review, mostly review. 10.1, 10.2, 10.4, and what I'm writing down will be the same section covered in the final. 11.1 through 11.8, all of them. 11.8 is Lagrange multipliers. That may or may not be on the actual midterm, but it's included in the midterm. 12.1 through 12.5, all of them. Skip 12.6, as you know, and 12.7 will be covered today. Will be covered today in the classroom after the review. Because today is a long day with almost 3 hours. I don't know, we have almost 3 hours today. I'll just do the midterm and then I'll move on to 12.7. 12.7 is the last required section in chapter 12. And then there is nothing else but chapter 13, and that's it. 12.7, you will see it's called cylindrical and spherical coordinates. And you use this type of coordinates for triple integrals. If everything is in 3D, three-dimensional Euclidean space. All right, is it clear? So, I'm going to start with the specification. Books and notes and portable electronic devices of all sorts are not allowed during the examination. No calculator, no pagers, no cell phones open. Taking this exam is subjected to the existing rules of texas regarding academic honesty. So don't attempt cheating, looking at the notes, talking to other people during the exam. That's not going to be allowed. Writing the spaces provided under every problem. No additional papers are to be turned in. When you'll actually get the exam, it's going to be typed a little bit larger. So you will have spaces between the problems. In those spaces, you will be able to write. The answers are really short. You'll be surprised how short they will be. On top of those 2 pages, there will be a third page which is blank. In that third blank page, you can scribble your computations. You will not have many computations to scribble. The space provided should be practically enough for you to write your answers. 2 or 3 of those 10 problems will have multiple choice answer. So you're going to ask me, what do I expect about that multiple choice answer? I will tell you in a second, and I will also give you an example. So I'm just expecting circling some numerical answer that you have there. And I'll tell you in the context of this sample what those are. Who's missing the midterm? Come and pick it up, please. And would you distribute this to the others? I'll take another one. All right. Number 1. Write the total differential of the following function. You will have something like that for a different function, but you will have to do the total differential. And remember, the total differential is not a sum of partial derivatives. If you want to kill me, say that. You're going to get a big 0 on that one, but you're also going to kill me in the process. So what was that total differential of a function of 2 variables? Now you know it, you can help me write it down.
Partial derivative in the x direction dx.
And that's an infinitesimal element. If you skip that, everything you write is nonsense. So pay attention that this part, the whole combination of scalar real value functions and infinitesimal elements will be in. Good, so what is the answer for my problem here if f is What's your problem? Let's see, what's your problem? Cosine of xy. So we have to compute, and I'm going to do this in line. I hope it's visible enough for the video. What's the derivative with respect to x of cosine of xy?
Negative y sine xy.
Negative y sine xy. So pay attention to the chain rule. You will have to remember that the derivative of this function with respect to x assumes that y is a constant. So when you differentiate xy with respect to x, y remains out of the product. All right, dx. We'll take the head and say dx. That's the infinitesimal element in x plus. What next? The same thing, it's a symmetric polynomial, but exactly like Aaron said, now I'm going to have minus x sine xy. So the same kind of policy. You've seen this before on homework. Guys, I don't like surprises on the exam, so what I picked for the midterm, and you will see also the final will be in the same spirit, it is out of those 200 problems, whatever you have covered in the homework. We don't give you new stuff that you haven't seen in the homework. All right, so with this, your answer is ready. You have one or two rows are enough for you to write down the answer for that. Actually, one line would be enough. Do I expect more than this line? Take one from the desk, please. So do I expect more than this answer under problem 1? No. If you know, you either know it or you don't know it. If you know the definition, you don't have to repeat it. If you know how to differentiate, you're fine, you're in business, you got a perfect score on this first problem out of 10. They are not time consuming. I don't like exams that are time consuming. They are not testing anything. Okay, so I want to walk you through the material, through many questions, so that I see what you understood and what concepts are well understood and which ones are not. Okay. All right, let's move on to number 2. That was number 1. Number 2. Number 2, it says, find the directional derivative of a function f of xy which is equal to cosine of xy. What do you see? I have already prepared you for this problem because it's the same function as before. You have computed f sub x and f sub y already. That should be helpful when you write the directional derivative. In the direction, and by direction we mean unit vector. Direction of something means unit vector. What direction do they say the highest ascent? Well, so this problem is walking you through the whole chapter 11 by testing what you understood. So what is the direction of the highest ascent for a function like that?
The gradient.
The gradient. So if you know what the direction of the gradient is, you're in business. At the point P of coordinate 0, 0, so P is the coordinate 0, 0. If such a direction exists, and you say, well, of course it exists, it's a gradient, justify your answer. All right? So when would it not exist?
If there's no direction of highest descent.
Right.
If all of them are the same.
Right. All right. So what would you have to write in terms of directional derivative for an arbitrary function? What do you like? What do you know about the directional derivative of a function at a point in the direction of a vector u? You can write the definition with limit, That's gonna be an expression like that, eating up all your space. But that's not what I mean. I mean that you have to know the theorem that says this is partial derivative with respect to x measured at the point P times u1 plus partial derivative with respect to y measured at the point P times u2, where u1 and u2 are the components of your unit vector that we talked about before. Now, when I compute f sub x at P, I have to say, oh, I know who f sub x is. But if I compute it at P, and P is 0, 0, my God, this is going to be 0, right? And if I do f sub y at P, and P is 0, well, you also know that the second partial derivative is 0. So at 0, this is going to be 0 as well. So the directional derivative is 0. Did I have to find the direction of the gradient? No, because in the end, you got 0. So it's always important to write down the final thing you want, the definition of the directional derivative. In the actual exam, you may have a different situation. Okay, so let's work on alternative one. Alternative problem like that. I'll pick an easy f of x and y. All of the examples will be easy, numerically, computationally. The point of coordinates 1, 1, and do the same problem for this different data. Who will be u? U will be the direction of the gradient divided, if I'm talking about the direction of the highest ascent, of highest ascent direction. Sometimes I may give you that direction, and it doesn't have to be the highest ascent direction. But in this case, it has to be, because the problem says so. So you have to say, what is the gradient in my case? Well, it's a cake. That's going to be 1 times I plus 1 times j divided by square root of 2. So u1 is 1 over root 2, u2 is 1 over root 2. And can I write the sub u in such an alternative problem? Oh, it should be easy. Well, it is easy. The first number will be 1, because that's the derivative with respect to x times u1, 1 over root 2, plus the derivative with respect to y, 1 times u2, 1 over root 2. All in all, do you leave it like this? Oh, you leave it like that and you get 100%, I really don't care, but what if the problem is formulated as a multiple choice? When we formulate as multiple choice with A, B, C choices like that, we'll never write it well. If we are normal people, we'll never write it like that. So what do you think the answer, the correct answer out of those possible answers will be in this case? One answer will be 0, one answer will be 2, one answer root 2. So what are you supposed to do? Just go to the answer that says root 2 and circle it. Do you have to show any work? No. But you only have like 2 such multiple choice problems. Everything else is show work. All right? Yes, sir?
How would that problem change if it was the steepest descent?
The steepest descent will happen in the opposite direction of the gradient. So it's going to happen exactly in the direction minus I minus j over root 2. And if you compute the directional derivative in that direction, you're going to have exactly the opposite of that, minus root 2. All right.
It says justify your answer. How did you write that?
Oh, justify your answer. Let me justify the answer. I'm going to say here. The steepest ascent takes place in the direction u corresponding to the gradient. delta f. Formula du bar f of p. Formula above is a theorem that was from chapter 11. You don't have to know which theorem, but you just write down this was a theorem. You plugged in, you got 0. For your sample, well, the actual midterm, it may be different, the same kind of problem, absolutely. So you have to say, justify your answer. I may or may not say justify your answer in the end, but you have to know this anyway. You have to know this part anyway, and you have to know this formula anyway. Okay, so justification is showing the formula in itself and explaining that the steepest ascent takes place in the direction of the gradient. All right? Okay. Number 2. Number 3. They're all related. They're all the same function. So I'm going to go ahead and erase this part. And it says find number 3. For the function f of x equals cosine of xy, as if we never saw that before, find the gradient. What are you supposed to write on such a problem to justify your answer? And also it says, write parenthesis, specify the equation of the tangent plane to the graph z equals f of xy at the point, I forgot the word at the point A of coordinates 0, 0, 1. All right, so let's say this problem has 2 parts, but they shouldn't be long. Number 3 says what? Find me the gradient of this function. What are you supposed to write? You have 2 alternatives here. Either you write f sub xi plus f sub yj equals minus y sine xy I minus x sine xy j, or this is up to you. This is how I would write the gradient. Some people prefer to forget the x and y. They don't write the gradient in standard basis. They assume it is standard basis, and they only write the coordinates in angular brackets assumed with respect to the standard basis, canonical basis. Whichever you want is fine. Are you guys with me? Any questions? All right. Is this hard? No. Let's see how hard is the next one. What do you think I have to do? I'm waiting for your input. Write, parenthesis, specify the equation of the tangent plane to the graph z equals f of xy. That graph is going to be the graph of a surface, right? Z equals f of x and y. They want the equation of the tangent plane to the graph at the point 0, 0, 1, which means I have to take x0 to be 0, y0 to be 0, and consequently z0 will be cosine of 0, which is 1. So it makes sense that point P is on the graph, or A is on the graph. A is on the graph. Good. At least I know I didn't make a mistake about that. How do we write the tangent plane when someone gives us the explicit equation of the graph, z equals f of xy, knowing that f is a function? How is this function? Well, look at it. It's C infinity. It has, it's differentiable infinitely many times, and all the derivatives are continuous. So we are really lucky. We don't have any headaches in this case. Both partial derivatives existed, they are continuous, so I'm going to write down the equation of the tangent plane. But not by myself, with your help, because it's been a long time, but you're not allowed to forget the formula. What was the general formula for the tangent plane in this case? Starting with a z. And I'll try to keep my mouth shut. Z minus the 0. Remember the linear approximation of a surface, curved surface with a plane? That's the linear approximation.
That's with respect to
F sub x. I want to say with respect to what? X and y at 0, 0. Good, we'll do that later. Times
X minus X0.
x minus x0 plus
F sub y.
r sub y at 0, 0 times
Y minus
y minus
y.
y0. But again, x 0 is 0, y0 is 0, z0 is 1. Now, we know more than that because I gave you a problem that's too easy, but I'm trying to do something impossible. F sub x at 0, 0, we already computed that and we noticed that was 0 and this was. So we are exceedingly lucky in this case. Not all the problems are so beautiful. The problems that we give in the exam generally are more beautiful than all the problems that happen in reality, in real life. Z equals 1 will be your answer in this case. What is Z equals 1? It's the horizontal plane that passes that Z equals 1. So that will be the altitude. And you're done. You have problem. What problem was that? Problem 3. Finished. They are short and they are, I guarantee even the ones on Thursday, next Thursday, not this Thursday, will be very easy to solve. I'm just testing you on the concepts. See, what do you remember from the concepts? So now you know that, write a note to yourself, so she expects me to know the equation of the tangent plane for the midterm and for the final by heart. Yes, I do. And I think compared to other things that you have to learn, memorize for your engineering courses, this is a piece of cake. You only have a few things that you have to memorize, very few things you have to memorize. All right, number 4, find the direction in which the function, I'm changing the function finally. I say function x plus y increases most rapidly at the point P of 1, 1. Well, in which direction is this function increasing most rapidly at 1, 1? In which direction is this function increasing most rapidly at 1, 1. That means that x0 equals 1, y0 equals 1. We've done this kind of thing before. We know the direction will be the direction corresponding to that gradient. But attention, when I say direction, what do I mean? Normalize it. Okay, all right. So gradient of f at 1, 1 will be 1 times I plus 1 times j. I'm not allowed to leave it like this. I will say the answer is u equals gradient of f over normal gradient of f, which is I plus j over square root of 2, which is the same as writing 1 over root 2, 1 over root 2. And that's it. So if x is this axis and y is this other one, I'm modeling it with my hands. The direction I'm talking about is the first bisector of this quadrant in your direction, in this, pointing out this way. Okay, if I want steepest descent, it's going to be in the opposite direction, right? Okay, I'm going to go ahead and erase. I don't have much space. Number 5. Is it the same problem? Yes. So let's keep this on the board. And 5. what is the maximal rate of change of the function f of xy equals x plus y at the point t11? There is another theorem. So how do I justify my answer in this case? There is another theorem that says the maximum rate of change will be the directional derivative. So the maximum rate of change will be the directional derivative of f in the direction u of the gradient nabla f at that point P. This is what I would have done as a student, because I think I would have remembered only the theorem without remembering that this is the same thing as what? The length of the gradient at that point. I think I would have forgotten that because I'm trying to remember who I was more than 20 years ago and see how I would have answered this question. Now, I think I would have gotten to the same answer. Nevertheless, I would have struggled a little bit, and I would have thought just in the middle of the exam, why in the world is that? Because I always found myself not remembering things in the exams, and I would try to remember why is that. So, by the way, why is that? The directional derivative in the direction of u of f at the point P also was written, I wrote it down before f sub x u1 plus f sub y u2. But you guys told me what that was. That was a certain scalar product or dot product between the direction of the gradient and the vector u. And I was grateful you told me that that was a long time ago. It was 2 weeks, 3 weeks ago, something like that. So we noted together that it's the same thing if you write nabla f gradient, dot product with u. But if u itself is gradient of f, well, over the length, let's write it down. If I'm talking highest Sn, then u itself is the gradient of f over the norm, the length of the gradient. So what is the answer? That is nabla f, not nabla f will be exactly the square of the norm, the square of the length, divided by the length. So I proved again, because I'm forgetful and I'm silly, I proved again that this maximum rate of change is exactly the length of the gradient. For somebody who is better than me when it comes to memorizing things, they wouldn't have had to do that. I'm just doing review. So what was expected from you if you studied and you're a good student? We expected only that you would write. The answer would be which is what? Who's telling me what this is? Square root of 2 piece of cake. So it depends on how much you remember, how much you understood from the material, and also a little bit of memorization just helps. If you're not able to memorize, you can always come up to the right conclusion, but it takes forever, and you don't have time, 1 hour and 20 minutes or whatever that is, 1 hour and 20 minutes to think too much. Okay, I'm gonna erase, what shall I erase? Number 4, maybe I should erase. And
No, it's going to ask you about number 4.
how?
On problem 6, it asks you about that one specifically.
And number 5 is asking you,
We just did number 5.
yeah, and the answer is root 2. On number 4,
Number 6 asked you about that direction.
it asks you about that direction. That's what you have to bring on the exam, like this kind. Okay. So again, the actual exam may ask you to do this by printing it out. And when it comes to which of those following numbers will represent the maximum rate of change? 0, 1, square root of 2, 792, stuff like that. So you would have to circle root 2 in this case.
Oh, that's not I was saying you might not want to erase number 4 because it's about to ask you about number 4.
Oh my God, you are deeper than me. Okay. Is the direction that you found at point 4 unique for the given point? Yes or no? What do you think?
No.
Well, okay. By direction we mean what? Not all the collinear vectors that go in that direction, but the actual uniquely defined number as that. Right? So you can write an essay based on unicity and uniqueness of that. Say, ma'am, did you say the direction is this? Some people use direction in other courses, like linear algebra. In linear algebra, you will see they say 1, 1, 1 direction. 2, 2, 2 is the same direction. 3, 3, 3 is the same direction. But I told you in the restricted case of this course, by direction we mean that, so it's unique. All right, what else do we have here?
Yeah, question on that.
Huh?
Why would that be unique if, like, it doesn't matter what the point is, if you're gonna get that?
For a given point. So once somebody gave you a given point, x0, y0, you have only one answer, which is f sub x at x0, y0, f sub y at x0, y0 in angular brackets divided by, I'm too lazy to write it down, but I will. This is the answer. So God gave you a point x0, y0, and it asks you, and a function, a point and a function, and the point is on the graph of the function. It asks you what is that direction, and it's uniquely defined. Okay? So again, in other classes you will see people who say, well, up to a change in orientation, I can go back to Amarillo if I was driving this way, it's the same direction. For us, no. So for us, that is exactly the opposite direction. All right. Compute the volume. Now you like this one, and I know you remember it very well. If you don't like this kind of question, I can switch to another one. But all the questions should be easy. Yes, ma'am.
I don't understand why number 6 is unique at that point. Isn't the gradient the same at every other point since the derivatives of f of x, or since f of x and f of y don't have like x's and y's in them, they're both 1. So is it not the same for the entire graph, look at any point?
No. Okay, if you take another point, okay, let's take this one, right?
But
Well, I
isn't
thought
it
it-
asking like specifically for the graph of x plus y?
Specifically for the graph of x plus y. Excuse me. What is that direction for you? I plus j over square root of 2.
Yeah.
Period. That's unique.
Okay, so it's not
Right.
asking for the point, it's asking for the function?
At the given point. Okay, let me eliminate this, is too philosophical. But it says unique for the given point because the point is still given as 1, 1. For that given point 1, 1, the direction is unique. In the sense, this is exactly what I wanted to emphasize, that in other classes they will say the direction 1, 1 is the same as the direction 2, 2 is the same as the direction 3, 3 is the same as the direction 1 over 2, 1 over 2. All the collinear vectors are the same direction. They point in the same direction. But in our course, this direction is uniquely defined as the gradient over its norm, especially to make it unique. We do that especially to make it unique. I'm pointing in your direction, but every arrow that I'm pointing in your direction could have any magnitude. And though in an everyday life speaking, in physics, ask anybody in physics, mechanics, they will say, it's the same direction pointing towards her, whether you call it this or that is the same direction, you're pointing in the same direction. Because they consider direction being all the collinear vectors. I consider direction only this, the unitarized vector. Okay? It's not even a mathematical problem, it's a philosophical concept I'm trying to make out. But I will erase it and then replace it with another problem that is more like the homework problem you had before. Okay, this one you had in the homework. Compute the volume of the tetrahedron x plus y plus z equals 1, situated in the first octave. And maybe in the actual exam I'm going to say, let's write up the integral of the volume without solving it or something like that. Let's do both, because I'm afraid that you're going to cheat, and you're welcome to cheat on this problem as much as you want, but I would like you to also show me the actual integral. So the volume will be how much? This is 1, 0, 0, 0, 1, 0, 0, 0, 1. The plane is x plus y plus z equals 1. Am I right? Did I put 1 or I put another number? Put 1. Okay. So you know how to cheat on this problem. You say volume is area of the base times the height divided by 3, which is a half, times a 1 over 3 is a 1/6. But what I'm going to get, I think I'm going to rephrase the problem saying set up the integral as a triple integral with or without solving it. If you show me the answer, you get extra credit. You don't have to solve it by hand in this case. So you guys showed me last time what the answer was for dz, dy, dx order of integration. And how was it, guys? Mr. X is moving freely. He's the only free man in the picture, because even he has bound limits, but he's free to move between 0 and 1 the way he wants. And y will go to x plus y equals 1. So y will go all the way to between 0 and 1 minus x, right? So let me write it down. 0 to 1. Next. 0 to 1 minus
Oh, sorry.
What is dy?
x.
I thought you were asking for the third one.
You're fine. I mean, this is, you can change. Actually, one time, I think last year, maybe 2 years ago, last year, we said to the students, without solving this, show the volume integral in 3 different ways by changing changing the order of integration. So you can have dz, dy, dx, or you can have dy, dz, dx, or you can have dx, dy, dz. So they had to turn their heads in many ways and rotate and see how it is. But it's a nice problem because it's very easy to figure out what the endpoints are. And the last endpoints, actually the first endpoint if you think of integration, 0 to 1 minus x minus y, because you see Mr. Z goes up like a helium balloon from the floor, and he hits his head here. And he says, I hit my head there because I'm between 0 and 1 minus x minus y. And that's the upper bound for Z. And you're done. And that's what I would, a problem, maybe the same problem. or maybe a problem like that, but not hard, okay? Number, what was that? Thank you. Number, yes,
Can you change the order of dx, dy, and dz?
yes. Do you want, okay, let's do one of them. You mean, yeah, of course I can, but do you want to see it?
Yeah, I want to see it, please.
1 dx, whatever I want, I can do whatever, dz, dy, or dy, dz?
dy, dz.
dy, dz. So z is still between 0 and 1. He is the guy to start with. Okay, so what do you think? If you want to do it like this,
Next one is a dy, that will be 1 minus x.
the relationship that counts in the first picture, in the first frame that you think of, is the relationship between y and z, right? So Mr. Z is free to move from 0 to 1, and Mr. Y is here and is conditioned by z. And you have to write down the equation of this line, which is y plus z equals 1. Are you guys with me? So y goes all the way from 0 to y minus z, and x goes all the way from 0 to what?
1 minus y.
1 minus y minus z, the same thing. So how can you be even smarter? Do you guys play cards? You know what okay, so it's like in cards that at the end, after king, the ace is coming, and after the ace, 8, 2, 1. So it's a circular permutation, in the sense that x can be replaced by y, can be replaced by z, can be replaced by x, and so on. So what do you replace in this case to make a circular permutation? Z becomes x, y becomes y, this is held in place, and z becomes, and x becomes z. So what I can do is just replace the x's by z's, and I'm done. And the x by z and the z by x. This is circular permutation. Have you heard of permutations before? You can write them even in matrix form. I don't know if in linear algebra they will do permutations, but they should. They cover permutations usually in higher math, in 3310, or in graduate school. They start with that in algebra. All right, I'm gonna move on. I'm thinking, I'm not sure what I want to do really, but I'm also thinking of proposing an extra credit problem. I will say maybe something like that. Y equals x, or maybe any one of the problems could be considered an extra credit problem. I don't know. The same idea of reversing the order of integral. I would like you guys to, where do they meet? At 1? Right. So keep in mind that I may not give you the points. I may only give you the functions. And you have to find the points where the two functions intersect, where the two lines intersect. And it's a piece of cake because you set x as x squared minus x is 0, x times x minus 1 is 0, so you have solution x1 equals 0, that gives you the origin, and x2 equals 1, that gives you 1 and then becomes a piece of cake. I may ask you to say the following. Find me the area of this beautiful leaf by both methods, or reverse the order of integration. Set up the integrals in both ways and get me the answer. I have no idea what the answer is. I used to know these things by heart, but I forgot. So you have integral from 0 to 1, integral from x squared to x. Am I right? 1 dy dx. Or, and now shut up Magdalena, let people talk, reverse the order of integration. What do you have?
Still got 0 to 1.
Still 0 to 1 for Mr. Y. He's happy about that, sort of. We have to turn our head and look.
Square root y.
Y squared is smaller. Yes, he wants to be on the bottom, and this is y. So I'm too lazy to write it down. If I have 3 people who will tell me what the answer is, please, I'll write the answer down. The area of this beautiful shape. Is it? Yeah, I need 3 people to tell me what it is. Because it's not that I don't believe you, I know you're a good student, but I need witnesses so I can sign the document.
The second one, the order of integration would not be from y to under root 1. Why did you write y squared?
X is between y squared and y. Y is between
Square root of y.
Square y.
Yeah, square root of y.
Oh,
Yep.
thank you. So x is square root of y. And x, thank you very much. I'm very happy. You told me and I believed you. See why you should never believe people. Square root of y. And this is x equals y, of course. Good. So very good. So which one are you going to do? This one or this one? It's easier to do this one numerically, quickly in your mind. Come on, okay.
Yep, 1/6.
Okay, so x squared over 2, x cubed, 1/6. So I'm sorry for not believing you, but I should have been.
That's still only 2 people.
Huh?
Still only 2 people.
Yes. All right. Don't expect something hard, but of course always check it. Check your work even if you trust yourself, because any of us can make a mistake. This was obvious. So you see, just think of everything you write down and think, is this what it is? Even if you know the material very well, you can make an algebra mistake anytime. All right. Okay. Number 8. Compute the area of the part of the plane which lies above the xy plane in the first octant. So practically they say lying above the xy plane, there is this part of the x plus y plus z. You want the area of that guy. There are 2 ways to do it. I would not feel like repeating it because it's in your notes. How did you do this? Okay, how did you do this by elementary mathematics?
It's an equilateral triangle.
It's an equilateral triangle of side L, and then you said area is L squared, square root of 3 over 4. How did we do that with the height? This is L over 2, this is L, this is square root of 3L over 2. We did the area, we came up with that. So the answer would be, L is root 2, right? This is 1 and this 1. So root 2, root 3 over 4 is root 3 over 2. But that's not how I wanted this solved, right? So I may say using the formula of the surface area, find me the area of the triangular surface in the picture. And in that case, what do I need to do? We need to know a formula, which is what? Which says double integral over the domain D, square root of 1 plus f sub x squared plus f sub y squared dx dy, where f is easy to pull out from here, 1 minus x minus y. Who is D? Who remembers who D is? D must be the projection on the floor. So for D, I say x is between 0 and 1. Am I right? Am I right? Y is between 0 and 1 minus x. This is x, y, and z. What is this number? Formulas we give on the exams usually piece of cake. This problem was picked so that z will be so beautiful in order for you to integrate quickly the square root of. What is this number? Minus 1 squared is 1. 1 plus 1 plus 1. Root 3. Square root of 3. And square root of 3 will multiply. Okay, what is the meaning of double integral 1 dx dy over the domain? It's actually the area of that domain. Say what, Magdalena? Remember that when you had double integral, you don't have to do the work here because double integral over domain will be easy to compute. 1 dy this is 1/2. So you cheat only in part. You pretend that you've already done the triangle area. Otherwise, you will say area of the D will be my hard worker 0 to 1, 0 to 1 minus x, 1 dy dx, and das ist
Square root.
yeah, so it's x over x between 0 and 1 minus x squared over 2, 0 and 1, 1 minus a half, 1/2. I actually proved what in this part? That the area of this triangle on the floor is 1/2, as if we didn't know that from school. But I have to pretend that I don't know the area, the pink area being 1/2. All right? Okay. In this review, where else do I want to go? I want to do this with your help. It's sort of like this problem before, but a little bit different. Can I go ahead and erase or? Okay. So I'll write it down, yes.
In this case, if the question says which lies above the x plus y is equal to 1 or something like that, then how would we go from that?
So you know that that's above because the plane intersects the axis of coordinates by this line, and by this line. Everything that lies above in this first octant, because if it said, oh, well, maybe it lies above the plane, but everywhere, then you will be in trouble because you get an infinite area. But in the first octant, you have a finite volume because your triangle coming from here all the way down, it cuts the planes and you get the only thing you have above the floor is this triangle. That triangle that you draw in your imagination. Because if I start drawing, they will fire me. Even if I have tenure, if I start drawing with the marker on the board, I'll get in trouble. Or maybe they make me pay like $10,000 fine. But you have to imagine this corner as being exactly that one, and those three being your 1, 2, and 3 lines. That's the only thing that's above in the first octave. All right? Note that you have no alternative. You don't have something like that below. Yes, sir.
I was wondering where the square root of 1 and then the partial root of x and partial root of y come from. Because
This?
yes, that part. Like I understand the area and everything, but I don't understand.
We've done that before, I'll tell you in a second. So when we computed this kind of problem, there was a surface and this was parameterized. And we proved that there is a position vector, and for that you have, imagine like a car with coordinate lines, and we said we want to approximate the curvilinear domain between, this is a mesh or a rectangular mesh, and then you have a curvilinear square, and the best approximation for the area of that curvilinear square was the parallelogram that had the velocities. So you have this kind of stuff. You have a delta x here, and you have a delta y here, but here you have r sub x, and here you have r sub y. And you say, I don't want the big parallelogram, I want the one that is approximated infinitesimally small. So you make pixels and pixels and pixels that are smaller and smaller, and you can say, if this curvilinear pixel is small enough, then its area will be what? R sub x, R sub y in cross product in length, which is the area of the parallelogram, times dx dy. Right? It's like delta x and delta y displacement. When we did the kind of, this is infinitesimal area. When we did the integral, we said, write Rx, Ry cross product, dx dy. And we say, oh my God, this is such a pain to write the surface area. That's going to be the surface area of the graph. This is the graph S from surface, area of S. We came up with this. If you remember, it was a long time ago. It was before the spring break. Okay. We took R as the parameterization, and we said, wait a minute, if R is my parameterization, it better be easy, otherwise my life is going to be too complicated. So I go, x is x, y is y, and z will be, instead of z, we put the graph, f of x, y. And then we did what? Then we said R sub x was 1, and this is where the 1 comes from. 1, 0, f sub x, R sub y equals 0, 1, f sub y. And when we computed the cross product, we got, what is the cross product, guys? I forget. IJK, the determinant that has IJK, and the coordinates on the first row and on the second row. So I'm practically proving the theorem. This is the theorem. Most people don't prove anything in the classroom. They just say, swallow these formulas, they come from God, you have to believe. Right? But the whole artificial argument was brought up by people later. The way Gauss and Euler, independently anyway, came up with formulas like that was by finding this curvilinear little red area of this curvilinear square written as an integral. And this becomes much more beautiful when you have z equals f of xy as parameterization. So what do you do in that case? Well, you take the length of this vector. What is the length of this vector? What is this vector actually? This vector should be, somebody help me please, minus f sub xi minus f sub yj plus k. Okay, so what is the length of this vector? The length of this vector will be exactly that. So this is exactly the length of the area of the little parallelogram, curvilinear parallelogram, that will, area element will be this. And that's why you have this area element. Let's call this area element. In general, it doesn't have to be so beautiful. In general, it's really ugly. It's an integral that you have to involve MATLAB in, or Maple, or something really hard. You cannot solve this by hand. Imagine even if you have a simple example, like, guys, think of the paraboloid. For the paraboloid that you like, that looks like a vase, what would be the parametrization? You would have to do square root double integral 1 plus 4x squared plus 4y squared. If you were to do that in a domain that's rectangular, you just kill yourself. With polar it's easy, but what if the domain is ugly? If it's a round domain, like a disk, on top of a disk you switch to polar and you say, thank God I'm above a disk, but otherwise it would be really hard. So what do you do when you cannot integrate because the integration is too hard to do? You go to MATLAB, which is written for engineers, but mathematicians use MATLAB a lot. Or Mathematica, which is primarily written for mathematicians, I think, by Wolfram in Urbana-Champaign, Illinois. And then, what are the softwares? Mainly MATLAB. MATLAB would be the one that helps you solve. And Maple, you can use Maple, it's very user-friendly. You can either, you just plug in the endpoints for the integral domain, and then you have the integrand to type. But MATLAB has much higher capabilities from computation of your points. All right. You can also write your own programs. If you are a computer science major, you would be able to program in C or C++, write a program on how to compute the area of a curvy linear graph above something. And that's neat. That's just for fun. Of course, you would neglect your other responsibilities, and you say, I'm not going to a Saturday party, I'm writing this program. And that's how we become nerds, by saying no to the parties. All right. So let's do this one. I'm not afraid. I know that you guys would do the problem with no problem. Over the interval, but I've never done exactly this one, so I want to see how you respond. Set up a double integral, it says, to compute the area of the domain between the two lines, so that you integrate first with respect to y and then with respect to x. Reverse the order of integration. What is the area? Remark that no written computation is necessary. Why? I don't know why am I asking that?
Well,
because it's an elementary problem. I didn't think of a graph, so the answer would be draw the picture, you will see how fun it is. Y equals x. Y equals x plus 2. It looks horrible. Guys, you have to forgive me. These are parallel lines, for God's sake. Okay. Do they look parallel to you? Let's say we are in hyperbolic space, and then they could be anything. Okay. No, now it looks okay. So you have x between. Did they say x has to be between 0 and 2? So this is the point 0, 0. This is the point 0, 2. This is the point 2 and 2. And this is the point 2 and 4. Okay. Set up a double integral to compute the area, then reverse the order of integration and tell me the area and tell me why I shouldn't have worried too much about the computation. So, integral from what to what? 0 to 2.
And x to x plus 2.
X to x plus 2, very good. Of 1, because it's an area, right? dy dx. Or reverse the order integration, but do it carefully, right? Is that easy? No, it's not easy at all. Why is this not easy? Because first of all, it's not easy because my picture sucks. Let's see what it is. I'll do it again. Oh, will you forgive me for this horrible picture? I'm gonna draw a better one. So first of all, this is a square. 2, 2. And this is 2, 4. And I'll draw the lines. Okay, now it looks better. Because before, your domains would intersect like crazy. So right now, I can see that if I want to do the strip test, vertical strip test, that's already done, and I'm glad with it. But if I want to do the horizontal test, I'm in trouble at first a little bit. Why? Right, so I have to split this integral into 2. So it's saying area 1 plus area 2. And so when you actually decide which method to use, you're never going to compute it with this one. Yes, ma'am?
Aren't they equal?
They are equal, but I'm saying when you compute, you don't take the worst. Well, you mean the 2?
Yeah. So can
Yeah,
you just
so you
multiply
can
1
say
by 2?
by symmetry. In this case, you're lucky. In this case, you're lucky. But what if in general, attention in the actual exam? Yeah, you can have something like that. So in general, you add them. You add them and you do like this. In this case, they are equal. So I'll write twice. But you have to say, observe that by symmetry we have to, the diagonal, this parallelogram, will divide the parallelogram into 2 congruent triangles. Yes, sir.
I don't want to sound dumb, but if I take integration between 0 and 2 and choose as the top function, my biggest function, then
0
remove.
to 2 this is the top function, this is the bottom function.
No, the
For
x
the
plus
2 to 4,
yeah, x plus 2.
this is the top function, that's
So
the bottom.
I take the integration between 0 to 2 minus integration.
Plus, no?
No, he's doing something different. I see what he's
Different.
doing.
Integration of 0 to 2 that is only in x.
Mhm.
There will be the same area that
You
is
mean
under
with
the-
respect to y or with respect to x?
I'm taking with respect to. I'm just looking at the graph.
Which graph? You look it like this or you
No,
look it
this
like
way.
that?
Whatever the graph is.
This way.
This.
No, x is between 0 and 2 or y is between 0 and 4 for you? Are you doing horizontal strips or vertical strips?
No, I'm just using the Cal1 base and finding the area.
Ah,
The 2
then
lines.
you're using vertical strips. Because this is the same as count 1, f of x minus g of x equals x plus 2. We haven't solved the integral yet, okay? So we didn't get to solving it. We are saying, how do I set up the reverse integration thing? Which I can say, observe congruent triangles, and then I say twice the integral from, this is 0 to 2. And then this guy is y equals x on top. This guy is, well, who is first?
There should be x equals y.
This is dx dy. Okay, this is dx dy.
X should go
So
between 0
x
and y.
is between 0 on the bottom and y on top. And you have a 1. And after you do this, you would double it. Right? This,
That's
what I
probably
wrote
easier.
is just, this part. So, in the end, which one do you do? Which one is easier for you to do? For me, what you said is the easiest. So you get right? So how would my son solve it? Or your nephew, by the way. He is third grade, fifth grade. Okay.
Just needs your
He would say, take this triangle, cut it and glue it here. He doesn't know parallelogram or anything. So he says, cut this triangle and glue it here. And he knows the area 2 times 2, and he would have got me in like 5 seconds. What we just discussed for 20 seconds. Now, unfortunately, life is not linear. Life is very non-linear. As you saw, you get the most surprising fight with the parents or a breakup, or that's all examples of life being non-linear. We have 2 non-linear functions, or we have some curvilinear functions that intersect. Elementary geometry is not going to help you here. Only calculus for everything that is non-linear.
That's why we have calculus.
That's why we have calculus.
Now, the question is,
Yes, I have a question as well, but go ahead.
would you accept if I use the column base, even though?
This is what my question was. Would I accept? What do you guys think? So I would like you to write this down because I'm saying it. I'm saying actually write down the reverse the integration and stuff. But if you don't do, just say, I see from the beginning I have a 4, and the area is 4. That's fine with me as well. I don't care how you get the answer. The simplest possible way to get an answer is the best thing, as long as the answer is correct.
So will there be partial credit on the exam?
And yeah, by the way, so what, like when I say set up a double integral, I would say at 50% to do that. And for somebody who doesn't know how to do that, I'd say, and the person says, I know it's 4, I saw it's 4, it's elementary, 50% partial credit. How, is that fair? I think so. So for setting up the 2 things, half, and for doing the numerical part by any method, half. And I do partial credit. All right. The last problem, the last of them on here. Write and set up only a triple integral in spherical coordinates. Now you cannot do 10 because I haven't taught spherical coordinates, and that's what I'm going to do today. In order to compute the volume inside the unit sphere, which is a sphere of radius 1 centered at the origin, we have to do that using spherical coordinates. And that's what I'm going to teach today. So, good. That was the time to stop. I'm moving to 12.7. Cylindrical and spherical coordinates. And you take a 5-minute break.
Right now?
Yeah, because it's sort of time to stop. It's between the review and the new thing to teach. How was your break? Good. Did you go to Florida? Or any nice place with lots of palm trees? You went home. That is the best. Always the best.
if it, did you go on a Christian school? My church went down there too.
Yeah, I heard First Baptist too. They went with the Navigators.
Hey Ryan, 6 and 7
It looked like everybody had a lot of fun.
The
Did you guys all work on the same project or
or
just
just like the library or something?
Different project.
Because like these are the...
Yeah, the city's crazy. It's kind of sketchy. Parts of it
Responded to it.
I wouldn't want to live there.
I thought that you were like open all your stuff, like that's cool. And she goes, sorry, I probably should have said your email address. Sometimes it's really awesome.
So like all of this was that hard. I just now learned what grading is.
Always a honey.
I didn't know what grading is. Like I didn't
Test, yeah.
But you see me have to just doing my work.
Why you Googling? Because there's.
It's a big day, Karen. It's a big
No,
day. We're watching
I said, what is the
You don't have to write.
There's a quote. Yeah.
Yeah, I feel like they're like so much yeah.
Yellow's nice too.
She draws smiley faces.
It's a highlighter.
Oh, that's so sad. All I can see
We can walk away here with the white.
definitely should right on the board.
Highlights what you wrote.
Buildings are still abandoned.
Anytime it goes to
Oh, okay.
It's still It's still Katrina.
The last person needs to sign this?
So we went down Bourbon Street and sat there.
Thank you very much for the attendance.
You gotta pay.
I went there over Christmas.
Now, if you remember polar coordinates are cylindrical coordinates, so they are the easier guys to learn. Practically, I'm talking about switching from x, y, z in R3 to back and forth to r, theta, and z. In which way? Well, x, y are your old friends, r cosine theta and r sine theta, and z is z. So this is the change between Cartesian coordinates and polar coordinates, and it's a differentiable function, so you can go back and forth. So who's going to be r as a function of x, y? Square root of x squared plus y squared. And then if you look at tangent of theta is always y over x. So theta will be arctan of y over x. So you have a bunch of inverse functions that are differentiable. Okay? Both functions are C1. The one that goes from r theta z to xyz and back. These are both C1 functions. Differentiable and the derivatives are continuous. So you have no problem setting up a Jacobian, not only the Jacobian b. That's going to be dx dr, dx d theta, dx dz. So you take the xy z prime with respect to r, theta, and z. Then you have dy dr, dy d theta, dy dz. So you can take this function of these three variables prime with respect to each of the three variables. And then you take dz with respect to r, with respect to theta, and with respect to z itself. And you say, oh my God, this should be easy because they are independent. Exactly. So you have independence here. This declaration of independence between x and z. So this is 0, this is 0, this is 0, this is 0, this is 1. He's a lucky guy. And these parts, you've seen these guys before. Let's see how well you remember them. You don't have to remember them. You compute them again. So if you differentiate x with respect to r, you get cosine theta. Taking x prime with respect to theta, you get minus r sine theta. Here you get y with respect to r will be sine theta. And y with respect to theta will be r cosine theta. And again 0, 0, 0, and 1. So who can compute this determinant and tell me quickly, well, if you are taking linear algebra and two of you are, you can tell me immediately.
R squared minus 2r squared?
It should just be r.
It's just r.
R.
It's just r. You can expand along the last row and you have 1 times the determinant over here. The determinant over here is just r cosine squared plus r sine squared, which is r. So it's r times 1, which is r. Your old friend r, which was the Jacobian for polar coordinates, is still the Jacobian for cylindrical coordinates. So that's why I'm saying cylindrical coordinates are your friends. They want to be your friends. Let me give you an example. Yes. Sorry, no. We take that eggshell from last time. We put it upside down. Only one eggshell, okay? We start with an easy problem. And this is z equals 1 minus x squared minus y squared. It's half of the egg that we built from plastic last time. And I want to express the triple integral of the volume. Express triple integral of the volume. In terms of first Cartesian coordinates, and second cylindrical coordinates. And you're going to say, well, I have a circular domain, right? The disk is a domain inside the circle. So it's a lot more natural to use cylindrical coordinates and not Cartesian coordinates. Why do you want us to use Cartesian coordinates at all? I just beg you to bear with me and not actually compute the integral in Cartesian coordinates, because you're going to kill each other in the process about the square roots you have inside. So you can go ahead and write it. Integral over d of the function on top, which is going to be, well, let's put it in triple form. The egg, e, you're going to laugh at me. It's the triple integral over the egg. But actually it's triple integral over the half of the egg, but I don't know how to denote half of an egg. It's all the volume of the body inside the egg. 1 dV. I can write it as a double integral over d, is that clear, of the z function on top, 1 minus x squared minus y squared, minus the function below, which is 0, which is going to tell me dx dy, which is also denoted dA. If you're going to do this in Cartesian coordinates, well, good luck to you, because you're going to have something like that. Mr. X says, I want to go between minus 1 and 1. And that's X. He wants to go all the way between minus 1 and 1. And meanwhile, Y says, but I'm restricted by you because I'm in a marriage. X squared plus y squared equals 1. So y goes between square root 1 minus x squared and minus square root 1 minus x squared. So he goes, look how ugly I am. Minus square root 1 minus x squared plus square root 1 minus x squared. And then you have to put the integrand, 1 minus x squared minus y squared. And then you go dx dy. So, it's not the best thing. It's not the most beautiful thing. Now you say, but I'm going to write it in polar coordinates, in cylindrical coordinates, and you'll see how beautiful it's going to be cut. And I agree. The same thing can be written as triple integral over the egg, over the half of the egg, 1 dV will be 1, 2, 3. What will be the volume element? Because the volume element is not going to be, when I switch to polar, not going to be dr d theta dz. It's going to be r times dz dr d theta. Remember that, because I've seen students forget this r, the Jacobian, all the time. This Jacobian is very important. All right, so I'll put here 1 r dz dr d theta. Mr. Z says, I know I'm going from the bottom to the top, from the bottom to the top. So Z goes, I'm between 0 and whoever you gave me, 1 minus x squared minus y squared. And he's happy about that. It doesn't look so ugly. And now R and theta say, well, we are sort of independent. R is always between 0 and 1 in my picture, because I have the unit disk on the bottom, on the floor. And theta is between 0 and 2 pi, because I have a complete rotation. If this were chocolate cake or just something made of something good, some mayo tower or something, cheese tower, and I wanted to cut it in half or cut it in a quarter, I would be very careful about the theta. For example, if this is chocolate cake and I cut it as a quarter, I have to say just the first octant. So you see the piece of the cake that would be in the first in our corner here. So for that kind of problem, you would have to say R is between 0 and 1, but theta would be between 0 and pi over 2. You guys with me? So you are lucky in this case that you have a full rotation all around, you eat the entire cake. But in other problems, you may have a half of a cake, a quarter of a cake. Yes, sir.
Why is it dx dy down there for the area?
dy dx, you are very smart, and I appreciate that. Thank you. In a regular class, okay, I'm not even saying. I made the same mistake one time just writing fast, and nobody noticed. I noticed later, but it was a little bit late. Thank you, I appreciate it. So this is y integration first, x integration. Good. Let's see about that. What am I gonna do with that? That worries me because this looks like it has nothing to do there. Everything should be in ZR and theta, and this guy is 1 minus r squared. Otherwise, he doesn't belong in there. So I have to write it down. 0 to 2 pi, 0 to 1, 0 to 1 minus r squared, r dz, dr, d theta. Is it hard to do? Is it hard to solve? Shouldn't be. Why? Well, let's go from the inside to the outside. First of all, what is the beautiful thing about this? As soon as I'm done with this integration, I have a product of functions in theta and r that are independent. So let me write it down. Integral from 0 to 2 pi, integral from 0 to 1, and I decide I'm all for it. I'll have integral of r dz. But z has nothing to do with r. So he says, well, I'm z, you're r, we are independent. R is like a constant for the time being. He can even go here and wait. And then the integral you have, he goes out, he gets out. You see, guys, he goes out. And then you have 1 integral of 1 is z between, I'm taking it slowly, between 0 down and 1 minus r squared up. I could have written this faster, but that's not the point. So this will be integrated with respect to r and theta in the end. So again, what did I do? I said that was the r. But the r, when I integrate with z, they are independent. So r gets out. Integral of 1 is z. Z between these two guys is 1 minus r squared. I'm going to write it down. Integral from 0 to 2 pi. Integral from 0 to 1. Your old friend 1 minus r squared times your old friend r, dr, d theta. Is this hard? Come on, this is not hard. This is a piece of cake. A piece of chocolate cake. Right? So, what is this? It's integral of r minus r cubed. What is your luck here? Theta is not in the picture, so theta says, I'm going to go out for a walk. You guys finish the integration in r. I'm by myself, 0 to 2 pi d theta. Say bye-bye because theta is not contained in the integrand. And then you go integral from 0 to 1 r minus r cubed dr. And now we have two beautiful simple integrals from Calc 1 that we should be able to solve in no time. I'm too lazy to write again the antiderivative, which would be r squared over 2 minus r to the 4 over 4. What do I get here in the end? 1/2 minus 1 over 4, right? So I have 1/4. Did you say the same thing?
I said 1/4. So
it's the same thing,
yeah.
1/4. All right, and this is
2 pi.
2 pi. So in the end, I allow you to write it like that. Of course, but you'll say, but it's silly. I should be able to simplify. Well, go ahead and simplify. How much do we get? Pi over 2. So this says that the volume of the chocolate cake, now I'm dreaming. Now it's not an egg shell that's empty in the middle anymore. It's just a chocolate cake all round up and made in the shape of a paraboloid or some hill made of chocolate mousse that I made. So pi over 2 will be the volume of that. Is this a hard problem? It shouldn't be. If you think about it, it's nothing new. It's all polar coordinates and nothing else. But you may want to see one more like that. Do you want to see another one like that or not? Yes, you want to see?
I did the same, but I couldn't get the right answer in homework. first level is Cartesian, and then you have to change the spherical, then you.
Algebra is a problem for all of
Yeah.
us. Did you remember to include the R and do everything
Yes,
slowly?
my issue was the borders, that
The boundaries,
no,
the
yeah,
limit
boundaries.
points?
It's not, if I put the 0, it's not right. So,
Send it to me, oops, send it to me from WebWork and we will see what I can do. It's still unsolved? Okay, I'll help you on that. All right, so let's move on
yeah, I tried pattern
to something, let's move on to something trivial. You are gonna say, come on, Magdalena, this is trivial, I don't wanna do that. Of course, I know we'll find it very easy, the volume of the can of Pepsi Cola or whatever. It's a cylinder of radius r and height h, and I want to set up the integral to compute the volume of the cylinder in cylindrical coordinates. So what problem is that? Problem 2 for cylindrical coordinates, to compute the volume of a cylinder. Did we know that from before? I have my helper here with, he has everything, you all know it. Area of the
Volume of cylinder.
base
Yeah, area of base of height.
times the height, which will be pi r squared h, right? This is what we should get when we compute the integral. If we don't, that means we messed up somewhere.
Well, we'll get pi r squared z.
Let's put big R because I reserve little r for the variable between 0 and big R for the polar coordinates. So this is big R and this is little h. And this is your domain. So how do you write cylinder? Well, let's say the body inside is called C. I have triple integral over C of 1 dz dy dx. Of course, we won't do this in cylindrical coordinates, so this dv becomes r dr d theta. No, sorry, yeah, r dr d theta dz. So I will have to do it in proper order. R, dz first, dd, dr, d theta, because, well, it doesn't matter in this case, z is still between some fixed values. Z is between 0 and h. Again, if this were a plane or another surface, you would write it as a variable function of two variables. Then you have r between 0 and r. You have theta between 0 and 2 pi. I could give you on the final or something a quarter of a salami, just cut the salami on the first octant and get the same problem as this, but instead of theta from 0 to 2 pi, you would have theta from 0 to pi over 2. All right? Okay. So, is this hard? It shouldn't be hard. R again gets out. He says, I'm out of here. I have nothing to do with Z. So Z is by himself. Z by himself gets integral of 1 dz. Z between 0 and h. So h is by himself. So I have again integral 0 to 2 pi, 0 to big R. And here I have h. Are you guys with me? Are you following? The r, the little r, d theta.
H can go outside everything.
And the r, I forgot. You see how easy it is to forget it. Oh, r is here, but I forgot it here. R is here. He was hiding behind the bush. So I pulled him back in the picture because I need to integrate with respect to y. Now, Fortunately for us, this is easy. It's a piece of cake. What is a constant for everybody? Little h. He goes out in a hurry. He says, I'm hurrying out. I have h out. But then you have a double integral of a product of two functions in one variable. So you have one integral in R only, which is this one. Are you guys with me? And one integral in theta only, which is integral of 1 d theta. Can you tell me the limit weights for the integrals?
0 and R.
0 and R for this guy,
0 to 2
and 0 to 2 pi for that guy. And now, it should be easy. And am I getting the right answer? What do you think? I am. Why? Because I have h r squared over 2 times 2 pi. 2 goes away, so I got exactly h times r squared times pi, which was the volume of the cylinder that our teachers gave it to us in K-12 with no explanation. They said, well, you have to understand it's basically, if you believe that the disk has area pi r squared, you multiply that, make h tiny sheets of that, then you multiply. And that's how we understood the notion of a volume, by repeating those cross sections. You have an altitude of h, and you have cross section after cross section after cross section. But still, you have to believe the area of the disk. How did we believe the area of the disk when we were little? I remember I didn't believe it. My teacher in 4th grade came up with some graphing paper. And we went ahead and compared what I got from the little tiny squares and the actual formula. And it was hard for me to believe, but I was surprised that I couldn't find an explanation for my pi r squared formula even in middle school, and then I started high school and still no explanation for that, so I was very confused. I was like, is math more like history where we have to memorize everything and believe everything? But thank God for calculus. As you said, in college I understood finally why the area of the disk was pi r squared. Okay. Let's move on to our friend that I announced today with lots of advertisement. Yes, sir.
What happens if you ask the area that is in between x and y plane?
Between?
X and y plane. What happens in that? You have the cylinders, right?
Between which plane?
X and y.
X and y plane?
No, yeah, let's say z and y plane.
Z and y, which plane?
This and this.
Z equals y? You mean x equals y is a plane?
Yeah.
You can ask, well, yeah. Let's say I'm asking the volume of the slice of the cake that is between x and x equals y plane, and this plane, what is this plane? X equals 0, and z equals something, flat.
Mm-hmm.
Then I have to think of again of so theta, right?
Mm-hmm.
I have to take pi over 4, 0 to pi over 4, and measure differently when I measure the angle,
Okay.
right? We will see some sort of measurements for angles that will surprise you. When we look at geography in on a map, on atlas, we see all those latitude and longitude coordinates, but nobody ever told us about the angles very well. How do we actually define longitude and latitude? Well, between mathematicians and people who work in geography, there is a consensus. Longitude is this thing that you measure around the equator. That is the angle. For people in geography, it starts at the Greenwich Village. through, I mean, the meridian that passes through Greenwich Village, I went there out of curiosity. And there is nothing there, it's like a suburb of London or something. It goes through, so meridian 0 goes through that, that's where you measure theta equals 0. And you go around up to theta equals 2 pi. And how many meridians do we actually have?
24.
So when we have them 1 degree apart, there should be 360 things like that.
Technically, they're infinitely.
But,
Yeah.
huh?
They're infinitely.
Yes, but how many do we define?
Yeah,
as
in geography we
geography?
say 0 degree, 1 degree, the discretely many, 0, 1 degree, and so on. So the one that's at 180, okay, it goes 0, 180, is the meridian that if we were to continue, it would go to meridian 0, past the North Pole, all right? So we have this notion of longitude that we are going to introduce from 0 to 2 pi, and that's fine. But how do you measure latitude? Longitude is okay. Latitude, in geography and in mathematics, they may differ a little bit. We can even change our notation of for latitude sometimes. In geography, always from 0, the equator. Going up at the North Pole, what is your latitude? 90 degrees. And how do we say that? Well, in math we say pi over 2, but well, okay. Now we say north, 90 degrees north in geography. For a mathematician, it's not like that. Mathematicians are crazy people. They go minus pi over 2, which is minus 90. The geography guy says 90 degrees south. Okay? What latitude are we here in Lubbock? Do we know? Come on, you know.
32?
Something, 33 I thought, but maybe I'm wrong. Some, like that.
32.8.
32.8? I don't know. In any case, when we measure latitude, we should always start, if we are normal, we should always start at the equator, because that's how we did it in school, right? To go this way and this way. Mathematicians, though, they say, no, I'm going like this. I'm going from minus pi over 2 to 0 and to pi over 2. That's one way to do it. One way. Minus pi over 2 to 0 to pi over 2. But here in calculus, we are absolutely not normal. So we have another way of defining latitude. We say latitude from the North Pole. Latitude from the North Pole. I know how to spell. So we measure like this. Look at me, you're going to be amused because you'll think that we are crazy, which is true. But this is already accepted as a notation. So we go like that all the way to 108. So this would be, the North Pole would be, so what is the angle for the point P? The angle for the point P of latitude, not theta, theta was the longitude, let's call it phi. Phi is between 0 degrees and 180 degrees, which is the South Pole. So we measure, I think because mathematicians still believe in Santa, I don't know, they go from the North Pole, 0, 90, 180. So this is the angle phi that we are defining. Let me show you on a picture what the spherical coordinates are, the way we are going to use them. So I take a big sphere. Big sphere. And these are the, well, I'm sorry guys, I messed up. These are the axes the way you know them. This is x-axis, y-axis, and z-axis, and the origin. And you pick your favorite point somewhere on the sphere. And you say, I want to see what spherical coordinates are. And those spherical coordinates are three coordinates, r, theta, and phi. R is the radius from P to O. Theta is the longitude, and phi is the latitude from the North Pole. North Pole. Okay, so let me draw, let's take this red, let's draw OP. R. But then we say, well, I mean, I could be inside the sphere. Yes, you can still be inside the sphere. It can be anywhere you want in space. Then, how do you measure the latitude and the longitude? First of all, to measure, okay, let's go from P down. And that's going to be P prime somewhere. And then I'm going to say that's OP prime. And then I will project on the x-axis and the y-axis. So I'm putting 90-degree angle, 90-degree angle. This is the x-coordinate. This is the y-coordinate. And this is, how do I do the z-coordinate? Through the point P, I should draw a plane. That's the point P. I should draw a plane that's horizontal until that horizontal plane is going to cut the axis z. I'm going to do that. And then what I get is something that finishes my rectangle. I have a 90-degree, 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 90-degree. And this is z. This is z. So we have to write down everybody, x, y, and z, in terms of our theta and phi. This is going to be just trigonometry. We are going to get a little bit of a headache, but I know that you are going to help me. So the latitude measured from the North Pole is this angle. This angle phi, which is the same thing as this angle phi. And where is the angle theta? I need a lime color. And I have it here. And that's theta. So somebody needs to help me. It's the easiest is z. Why is z the easiest to write down? Because it's going to come from the Pythagorean theorem for whatever, for trigonometric angle phi. I have a 90-degree, and this is the triangle. What do you think z is going to be? I have an angle 90 in this triangle. I have an angle phi. And z is the adjacent. R is the hypotenuse. So let me write it down. Z is R cosine phi. Yes, in this case. Why is that? Because I'll take z over r, and that's cosine phi. Z over r is cosine phi, is the adjacent over the hypotenuse. All right, that was easy, but the problem is, how do I get to x and y? Unless I find the projection, now I need you to give me the line OP prime measure. This is the not harder. It's from this other triangle. I'm gonna fill it in red dots everywhere.
That line is r sine of phi.
R sine phi. Why is that? Because sine of phi will be exactly the Where is the 90-degree angle? Here. So the sine phi will be the opposite over hypotenuse. Say it again. Opposite over hypotenuse. And that's the 90-degree angle. So good. So it's OP prime over R. Good. But now I have to go on because the lime guy is not the end of the game. The end of the game is X and Y. So X is OP prime cosine theta. Y is OP prime sine theta. Who can tell me why?
Because X is your adjacent and Y is your opposite.
Right, because this is also 90-degree angle. So I have a right triangle. And if I take the angle theta, this is adjacent for the angle theta. So cosine theta is X over R, X over OP prime, the hypotenuse. So again, let's write X over OP prime is gonna be cosine theta. Y over OP prime is gonna be sine theta. And that's why I have those. Good, so can I write X and Y? X will be, now comes a little bit of headache. OP prime is R sine phi cosine theta. R sine phi, not sine phi, sine phi, cosine theta. Y equals R sine phi, sine theta. And Z equals R cosine phi. Good. These are the famous cylindrical, spherical coordinates. Spherical coordinate transformation. So what does this transformation do? This transformation takes the R, phi, and theta and moves them into the image X, Y, Z. So this is the transformation I was talking about.
No, doesn't it go from X, Y, Z to R?
It goes back. So you have a one-to-one function, you have an inverse, and the inverse is also C1. They are both C1 functions. The inverse, who is the inverse? Oh, I don't know, guys. Okay, I only give you one piece of information that's crucial, and you have to find phi and theta, which are not hard to find. Who is R?
R is still X squared plus Y squared.
R
Plus Z
is X squared plus Y squared plus
Z squared
Z
square root.
squared and the square root. Let's see why that is. You may not believe me, but I'll do it. So assume that U square X squared plus Y squared, right? Then you have R squared sine phi squared, but the square of this plus the square of that collapse and will become a 1 when you add them up. So when you add up X squared plus Y squared, this goes away and becomes 1, and you have R squared sine squared phi. Now, if you make Z squared, who is Z squared? R squared cosine squared phi. Add them all up, X squared plus Y squared plus Z squared equals little r squared. Little r squared. So, now we are ready to prove the volume of a ball. We have this is a ball of radius r. Ball of radius r. Find the volume of this ball with any kind of coordinates you think. But now you'll say, okay, if you do cylindrical coordinates, good luck to you. It's going to be, we stay here until midnight and computing the volume. Let's try both and let's see how they differ from one another, how hard they are.
Can we do Cartesian?
I'll write Cartesian, but I'll write Cartesian, I'll write cylindrical. I'm not going to use them though, I'm going to say goodbye to them. And in the end, I'm going to use spherical. Now, the beautiful thing about the Jacobian for spherical is that it has to be memorized. Because for you to write it down as a determinant, dx dr, dx d phi, dx d theta, and there are 6 more like that. It takes forever. So it's better that I tell you what it is. I computed it a few times, and we get r squared sine phi. So what is the volume of a sphere, the volume of the ball? I can write a triple integral of 1 dv over the ball B. Let's call this ball B. Script beautiful B. And that will take care of this dx, dy, dz, right? That's the first formula. I cannot use it. It's gonna be a mess. Now let's try this written at least in cylindrical coordinates. You will still see that it's not easy. When we write it in cylindrical coordinates, I'm gonna have cylindrical coordinates still. It's gonna be what? It's gonna be an R, and then dz, dr, d theta. And z, well, we can do what Bexat said, what Matthew or several of you. When you have a symmetric object, you split it in half and you say double the area. We can always do that. Or you can go from the southern hemisphere to the northern hemisphere, and you practically get the same thing. Now, for the ball we have here, you have x squared plus y squared plus z squared equals, what was the radius of the ball? R squared. Okay. I don't like it, but that's okay. Z will have to go between what and what? Between two nasty square roots and a minus. R squared minus x squared minus y squared, and r squared minus x squared minus y squared with minus. Do I like it? No, but at least that's in Cartesian. At least in polar coordinates, I can say Mr. Z decides to go from minus square root r squared minus r squared, because x squared plus y squared is cylindrical. This is r squared in cylindrical. Okay? So I would do it like that. Square root r squared minus r squared. R from 0 to r. And beta from 0 to 2 pi. And I don't want the headache of these square roots, because as soon as I do that, well, I can do it, but it's obnoxious. I take the z out. Z between the two. I'll take z between this and that, so I'll have twice the square root times little r. And I have to perform some U substitution. I have to be smart, and I think I can do it. This is in cylindrical. But I want to show you how beautiful it is in spherical. In spherical, what are you going to have in spherical? In spherical, you have this, the ball in spherical. One, two, three. Of 1. 1 times the Jacobian. Who is the Jacobian? R squared sine phi. Good. What else? Anything else you want? The r, the phi, the theta, they are all between fixed endpoints. So you're really lucky. Why are you lucky? Because all these guys, r, phi, and theta, are between fixed endpoints for a ball. Do we know those endpoints? Well, we better. If we don't, then we are no good. So r for the ball goes little r from 0 all the way to r. Good. Now, the latitude measured from Santa Claus. That's the question. It's pi, right? It's from 0 to the South Pole, pi. And theta is from 0 to 2 pi. From the Greenwich meridian all the way back. Good. So now we are ready. Now it's a blessing because we apply the Fubini theorem, and all the endpoints being fixed, I can separate this integral into a product of 3 integrals that are all independent. And I'm going to ask you to tell me what those are. Yes, sir.
Why don't we just go from 0 to pi with
You mean for phi? Okay, the phi is the latitude measured from the North Pole. That's why I said Santa Claus. Because mathematicians, many of them, are split into two categories. They say, some say I measure latitude between 0 and pi and 0 minus pi over 2. So I can go all the way between minus pi over 2 to pi. But some say no, I don't like it. I measure the phi from 0 because it's easier for the picture. And I measure phi from North Pole all the way to the South Pole. And the latitude goes all the way to pi, 280. Now for me, it was easier because I was able to draw this picture and I was able to write those formulas very easily. Now, for those integrals, can you tell me the first one in R? Who can tell me the R?
0 to R squared U.
Very good. So that's the only thing that's a little bit harder. Everything is easier. Integral from
0 to pi,
1 sine phi d phi from
0 to pi.
0 to pi. And finally, integral from 0 to
2 pi.
2 pi
Just d theta.
of 1 d theta. And you say, and that's just 2 pi. I know, that is the beauty of it. It's 2 pi. So this simplifies a little bit my life. How about the first fellow? I know you love the picture, right? You love this picture. But I need to say goodbye to it. Okay, so I'll erase it. And I have r cubed over 3. R cubed over 3 starts showing the meaning of the volume formula that you knew from high school. So this guy becomes r cubed over 3 means big R cubed over 3. Here, the first guy. This first guy is this first guy. This guy, not a problem. Integral of sine phi is minus cosine phi, and that you have to measure that between 0 and pi. So you have to do it a little bit carefully. At one time I had a student who got 0 on that. After he plugged in here, he got a 0. So he came up with this new theorem that the volume of the ball was 0, no matter what the radius was for kid. But he didn't realize what was going on. So you realize what his mistake was. He didn't get the signs right. So minus cosine of pi. What's cosine of pi? Negative 1. With a minus is minus minus 1, which is plus 1. Right? But then you have minus and he wrote 1, and this is where the mistake was. Minus the other one is minus cosine of 0, which is minus 1. So you get 2. All right, and then finally 2 pi. So what did we get here? We got something beautiful. We got
4/3 pi r cubed over 3.
huh?
Or 4/3 pi r cubed.
Yeah, we got 4 pi r cubed over 3. This is the thing we knew from when we were little. How old were we when our teachers told us that they cannot tell us why, but this is the volume of a sphere? Were we in 9th grade?
I was
Younger? 8th grade? But I don't think I was able to memorize. That was one of my problems. I think in 8th grade my teacher gave me the formula, but I wasn't able to memorize that in 8th grade. And I think in high school I memorized it finally, like when I was 16 or something. So this is 4 pi r cubed over 3, and it closes that question. Next time I want to do 1 or 2 more applications for the spherical coordinates because you're not yet used to them. Maybe I'm going to do a mixture of the problems, cylindrical, spherical. You know what to expect. Don't expect anything really hard. But it walks you slowly through the whole material if you go over the set. Okay? Enjoy the day and ask me questions if you have. I'll be in my office hours.